In this video, we are going to talk about how chips are designed. We are going to have a look what tools are used and how exactly it is done, correct?
Yes, that's what we're going to do. So my focus is mostly on analog and really ASIC design. And so we're not going to look at the digital side. I think you've done some videos on that also in the past already. But this is full custom ASIC design with analog and millimeter wave, which is what I do. And we're really going to look at how the tools work and how the tools are different from what you might find on the PCB design, for example, and how the flow is different.
Okay. And what is the difference between digital and analog? So I think last time you mentioned digital would be like kind of, there will be a lot of automation and auto routing.
Yes.
And okay. So analog is more complicated.
Yeah, if I say yes to answer yes, then I'm gonna annoy every digital designer ever. It's complicated in a different way.
Okay.
So digital design is a lot of it is done on a higher level. So it's similar to software where they program in something like Verilog or VHDL, and then you have tools that turn your logic design that you've written in code into actual gates, and then these connections are to a high extent done completely manually, automated. I mean, sorry. So for example, I actually have a cell here in a different technology of what such a digital design would then look like.
Okay.
Right. So you have the sea of gates here. So if we zoom in and zoom in and zoom in, what we see here is on a very low level, each of these things here, so the orange bit is a transistor.
Mm-hmm.
So here, these are all transistors or parts of transistors. And then they're built into cells. And you can see this grid approach, and then a tool will translate your logic into, or your design into gates. It will place these gates and automatically connect everything. But we don't do that in analog. In analog, we really go and we take this transistor that I can show you here. For example, this is a very simple transistor. With in red is the gate. Then we have a drain and a source, or we can flip them because it's symmetrical. It doesn't really matter. And we, as a designer, we can choose everything about this transistor in terms of its dimensions. So, for example, this is a very small transistor. If I look at this transistor, this is has a gate length of here. Come on. There's a 45 nanometer gate length, so it's a tiny device, and it's 120 nanometers wide. But as an analog designer, I can make it wider. So now, if you think about it, it's like we place more of these transistors in parallel next to each other. I can make it the gate itself longer, so we put more in series, and you can go to very high extremes here. So if you compare the size of this transistor to this guy here, we have this flexibility to choose this, and we want to choose this because one of the main differences between designing analog circuits on a PCB level and designing analog circuits on a chip level is that we cannot, I'm sorry, Google is complaining right now, is that we cannot use resistors in the same way because resistors are absolutely horrible. So I have a slide if you want me to show it of a simulation I did with resistors.
Like we will go back to resistors.
Okay.
So first, I think my question would be, what is difference between these transistors? Do you change parameters like higher current can flow through this? Okay.
Yes. So so when you think about designing an analog cell, what you do is you play with output resistances, input resistances, the gain of a single transistor, and you want, if you have multiple transistors in a cell, for example, here in an op-amp, a very simple OTA here, right? So you design this schematic, and this is every analog designer learns this is one of the first cells you see in IC design. It's a differential input pair here with a current mirror load and a current mirror as a tail, right? So you design this schematic topology, and then you can, if you do lower speed analog, you can really go into the hand calculations and calculate, I want this gain. So then this device needs this output resistance, this device needs this GM, what we call it, so voltage to current conversion. And then from that, we can calculate the gain. And so to do that, to get a certain output resistance, you might make the transistor longer, because then, of course, it makes sense if you think about it. If you put more resistances in series, right, you get higher output resistance. In order to get more current capacity, we might make the transistor wider, because then it's like putting more of them in parallel. And so you get more gain as well, because a same gate voltage is now multiplied by a larger amount. And so that's really the art of analog IC design, is that we need to balance all of those factors and understand the limitations of those factors to design our cell.
Okay, I have a question.
Yes.
So this schematic is basically the schematic of the chip, correct?
Yes. I mean, of a very simple chip. If you make a full large ASIC, you might have hundreds of these cells. That's the magic of chips, is that we can fit a lot of transistors on a single piece of silicon.
So it's basically, it's very similar to drawing schematic for a board.
Yes, indeed. I mean, conceptually, it's the same, right? We're still connecting devices with wires to each other. And we also route these wires in metals. So in that sense, it is the same. And then we take these components, and we would then go and make a layout out of this. And I'll here open an example.
So I guess there are also some libraries which are created from these symbols which you use, and then basically from the kind of process or materials or something what is kind of, it's not
exactly
in PCB, it's footprint, but in this chip design it will be some kind of
yes. So indeed, so these cells, these transistors that you see, they're provided by the foundry in a big library. This was called the PDK. And so in this library, they design their technology, and in that technology, they might have a number of what we call threshold voltages. So it's kind of I mean, you know what the threshold is? It's when the transistor switches. And then they might have a number of oxide thicknesses. So a higher oxide thickness gives you a transistor that can handle a higher voltage. So you might have a transistor here that can only handle 0.8 volts. So you can, no terminal of these transistors is allowed to see more than 0.8 volts, but you might have devices for IO voltages that can take 3.3 volts or 5 volts and so on. And so they make this library. They add design rules to this library. So how am I allowed to design my layout to work with their technology? And then they wrap this all up and call this a PDK. And this is what we then use. So this is what we install. And so in this case, the PDK that I'm using is an example PDK, because Global Foundries or UMC or TSMC wouldn't appreciate it if I showed you this proprietary information.
So these are you call them these are these companies what do okay.
Yes.
So these are companies what are manufacturing the chips.
Exactly. So I designed it, and then I send it out to them for it to be made for me.
And they give you the libraries because
so I can design in their technology, right?
Okay.
And so this is, for example, this example technology, and then we have a list of types of components we have. For example, here this is FinFET. So we have these transistors with a number of threshold voltages in NMP variety, and then these are parameterized, so I can make them larger, I can make them longer, so on. And then I use these to make my design.
Okay, and then you need to, if you change the parameters, do you need to like simulate it then? Because how do you know what happened with the transistor when you change some parameters?
Indeed, we have to simulate all of this, and that is also what they include is what we call usually it's using BSIM, which is this very complicated model. I think it's more than 200 parameters for a single transistor, and then so they provide this as also as part of the PDK. And so, for example, here this OTA I just showed you, this schematic, I can then put it into a test bench, right? So this is that cell I just showed you before. And I connect a load resistor and some input sources here, a supply, and then I set up a test bench for this. I will organize my windows here nicely. Voila. So then this is a test bench, and in this test bench, I say I want to simulate this design. So I go here and I say, the design I want to simulate is this test bench and the schematic view. So you can see here, OTA test bench schematic. This is what I want to simulate. I set up which tests I want to do. So in this case, I do a DC simulation for it to calculate the DC points inside of all of the transistors, and then AC simulation to see the gain and the bandwidth of my amplifier. I can add some variables here. So for example, this bias current, you make it a parameter so I can sweep in and more easily design with it. And then I have some specs that I have. So in this case, I've already defined them before. So for the DC gain, I want more than 10 dB. I want a 3 dB bandwidth of over 200 megahertz and so on. So you define these things. Then I can now simulate this.
And it will then tell you if it passes or fails?
Exactly. So if we give it a few seconds, it'll now do all of these simulations. It shouldn't take too long because it's a very simple cell. So it first net lists and then simulates. And then voila. And so now it's telling me, so I'm varying the bias current. And so it tells me, look, the gain seems to always be good, but I don't meet my bandwidth here on the lower bias current. But then if I go up and I see here, starting at 7 microamp of bias current, now I do meet all of my specifications. And then as a designer, right, based on this, I can now also go back into my cell. I can play around with the transistors, maybe add some more transistors, change the topology and so on. And then I do this for every cell. And this is how we make our design. So we can simulate it into incredible detail because of this, with this PDK and the information in there. And so once I have this in schematic, I can then, for example, send this to a layouter who will then make my layout, or I can make my layout myself. It depends on the company and what you're doing. Yeah, that this is the flow for a cell.
Okay, I have a question. Okay, so what kind of tool you are using? This Cadence, but it's not like Allegro or something. It's
no, this is Virtuoso, which is their analog IC environment. So it is. I have two open here. I have to check that I opened the right one now. So specifically now I'm showing IC Advanced because it's FinFET. And so they have different versions, and depending on the features you need, you get a different version. I think it's a bit like OrCAD and Allegro and so on. And this tool contains, Virtuoso is the platform. And then within Virtuoso, you have lots of different things because you have the schematic editor is one tool. The layout editor is another tool. And again, you have different grades. The simulation tool is another tool. And the simulation tool that I run here, so Maestro is what it's called, is different from the simulator engine that is used. So the tool is the thing that here shows me my interface, gives me these functions. The simulator itself is a different thing that runs in the background. And what my simulator tool here, so this window does, is it just gives that tool. So in this case, it's Spectre, which you can also say here. It just gives Spectre a netlist, and it says, go and simulate this type of simulation. Spectre does this, and then when it's done, it will hand these results to Maestro, and Maestro will then allow me to plot and probe these things.
And Spectra is also from Cadence?
Yes, Spectre is also from Cadence, but you could also simulate with tools that aren't from Cadence. So I don't know if that's set up for this PDK now, but for example, you have HSpice here, you have Ultrasim, AMS, and I believe HSpice, for example, is not by Cadence. HSpice is, I think, Siemens. And so it also depends on which models the foundry provides. So the provider of the PDK might give you models that work in PSpice and HSpice and Eldo, and then you have to use the right simulator.
So the chip manufacturer is kind of the library of the chip manufacturer will provide models only for specific simulators, and then you need to use these engines to simulate the.
In general, the very big foundries, they will provide the needed models for all of the simulators. And there might be other reasons why you want to use a specific simulator. You might have a simulator that's more optimized for RF. So we have Spectre with the Spectre RF options, and it includes a lot of simulation tools specifically focused on RF and millimeter wave simulations. You have AMS here is a simulator that focuses on mixed signal. So it might use simplified models of devices that are good enough for when you have very large simulations with digital blocks and analog working together. And you don't care if this digital gate is using 10 picoamps or 10.05 picoamps. What you care about is the functionality of your ADC. Then you might use a different simulator that is optimized for that specific situation.
I guess you would like to always simulate this because it can cost a lot of money to manufacture it and then find out it doesn't work.
Yes, it's very expensive. Well, if you want me to go into that specific part, for us now, I still work partially with the university, and so we're part of a university program, and we get big discounts. And so for us, if I'm working in, say, a 14 nanometer FinFET technology, you pay per square millimeter of chip area that you tape, and we do an MPW. So what they do there is they make a very small amount of chips, and they combine lots of designs from different companies all together on one wafer, so it's cheaper. And then for us, I think 14 nanometer is $24,000 per square millimeter, and then we get 100 samples. If you go to your fully own tape out in 14 nanometers, you're looking at a few million US dollars for a mask set. Of course, with these masks, if you go to volume, you can make 1 billion chips, right? That's the magic of chip design, is that scaling in volume is very easy, but that upfront cost is very high. So you want to make sure that your chip works, right? If you factor in the 20,000 US dollars per square millimeter, if you have a digital chip, that's 10 square millimeters. That's still $200,000 that you are paying for a single run. And if your chip doesn't work, that's money wasted, because you cannot add a bodge wire on a chip.
Yeah.
I mean, you can if you really want to, and there's techniques, but they're very expensive as well.
So what if someone would like to go into chip design? The best is what? At university, I guess. That's what you did, correct? That's how you learn designing chips.
Yeah. So there's a lot of universities that have an IC design program. For example, my University of Leuven, Catholic University of Leuven, they have a specific IC design program, both for digital, analog, and RF. And so if you do that program, you also do some tape out. So you actually, during your studies, you will make a chip, and the best chips, the students are even allowed to measure their chips, right? So that, I would say, is the best route to take, especially because a lot of these deep down analog things is not necessarily something you learn in very general electrical engineering. Like really the nitty gritty of a transistor and length and width, it's a specific field.
And if someone would like to just play with this, are they also some open source tools, or they need to go? I guess this one is expensive, this Cadence tool.
So Cadence is very expensive. I believe Google is actually working on enabling also open source analog design, similar to their project for open source digital design.
Okay. So if someone would like to learn more, they can maybe search for this Google project then.
I think that, yeah.
Okay.
And show Google that they're interested.
Okay. Now let's continue in this. I'm very curious. So we have schematic, and what do you do next?
Okay, so in this case, I've now I tested my cell here, and for example, I see like, oh, if the bias current here is high enough, then I meet all of my specifications. That's good. So now what I would do is then I would go into going to layout. So similar to a PCB, right? You have your schematic here with your cells, but now you actually need to do the routing. And so this is my example layout here. And so I will now place my transistors. And so I can start, I have a transistor here and a transistor here that I can place.
So these two projects are somehow connected?
Yes, so the tool understands this.
Okay.
So it understands that this layout is connected to this. And I can also, if I now select normally this transistor in the layout, you can see in the schematic it shows up, and vice versa. And what I'm actually going to do is I'm going to switch to this technology because it's easier to understand what's going on, because it's not FinFET. Sorry for the confusing switch.
No,
I'm now
no.
moving from FinFET to a 45 nanometer technology. And so again, I can launch it like this. Okay, so I'm opening my layout.
And what was wrong with the previous project? It was using different technology?
So that was using FinFET, and with FinFET, there's a couple of things I want to show that are very unclear if you do not at all understand, like if you're new to this, because you're working with fins. Whereas here, if I now place a transistor, if I have, for example, played this transistor here, so this is really a top-down view of a transistor with in red, these are the gates, these are the sources, and these are the drains. So these are the recognizable terminals. And so I would place these, and then I can even do interesting things if I want to with what we call interdigitizing, but I'll show that maybe later. Keep it simple for now. I will also place this transistor here. It's now
How
a very long
different they
transistor.
are. I thought
Yes.
they look like same in schematic and
Yes, and so that's actually one of the interesting things is this transistor is folded. So this is a very long device, which is very inconvenient to work with. So what I will do now is instead of making it one finger, is what we call them, of 10 micrometers, I'll make it 1 micrometer finger, but I will place 10. So now you can see it's the same length. And so all I did is I broke up that very large device and I cut it into pieces and put them next to each other.
And then you need to connect the
yes.
source and
so exactly. So for example, I can now I can even tell the software, like, please already make some connections for me. So what you can see now, it's placed here.
Okay.
In blue, in metal 1, it's placed these connections. And if I then start routing, voila, and it'll then tell me like, you have to connect this there. And now that's connected. So I would go and do these connections in all of these metal layers. And then what's very important in analog design, and I think also becoming more important in digital design, is that we then need to do a parasitic extraction. What a parasitic extraction is that we have now all these metals that we've added, and they add little resistances and they add little capacitances. And they will influence our bandwidth, they will influence our gain. And so we need to know how much influence this has, especially if you're going for high-speed design. All of these little capacitances, they will slow your circuit down, they will load your outputs. And so what we then do is we do a parasitic extraction. And so this is a very long simulation with a tool, again, with information provided by the foundry. And it will look, for example, if you have if I now create another wire here. So it'll say that there's a capacitance between this node here and this node here. And then it will make a new schematic where it will place this cell here, and it will add all of these new capacitors and all of these new resistors. And then I can go back and I can simulate, again, do the simulation I just showed you, and see how does my performance change.
So you don't really simulate the chip itself, you always simulate the schematic, but together with all the extra components which are created by the layout of the chip.
Exactly, yeah.
How do you know how thick tracks, wires, I don't know how you call it?
You mean these wires?
Yeah, wires. How do you know how wide you can create them, or is there?
So that's provided by a design rule, a big file, a design rule. I have it, for example, open for this technology here, and so it's a very long document. In this case, it's I think 100 pages for this example technology. But I mean that's very small. So one of the real world technologies I work with, this file is like 870 pages long. Because they also did, and this file then tells you, you are allowed to place a metal 1 line this close to another metal 1 line. But it's not just that simple, because then it'll say, okay, but if your metal 1 line is this thick, you actually have to place it a bit further. And if your metal 1 line is even thicker, you have to place it even further. And if the metal 1 line happens to be above a transistor, that might change even again. And so you have these tools that understand these rules, and then you run a DRC check on
So
this
they will
tool.
give you some kind of file
Yeah,
which you can upload, and basically all the rules will be set up automatically. You don't have to set them manually.
indeed. So I have this cell, a different cell again, and I can then go here and say, okay, let's run a DRC. And it's now knows I have to say, oh, okay, this is my technology. And this is the cell here. So I say like, oh, this is where you have to run, how you have to run, and so on. And then submit this. And it will now run. It will then give me a list here. So now it says, okay, I found 3 errors, right? And so this first one here, it says here, okay, so it highlights here, you added this blue shape right here in between. So this blue window here, it says like, this is an error here, this is a problem. And it says specifically, so the minimum M1 to M1 space is 0.032. And if I now measure from here to there, you can see it's only 0.01, so it's 10 nanometers, it's too small. So let me align it to the correct distance. There to there. Do it correctly? I think so. And then rerun.
So you moved it?
I moved it. So this is now a bit further. So you can see before it was 0.01. And now you can see this error is now gone. So I fixed that error. And so these other errors we're going to ignore. But that's, so you would do this for the entire cell. And when you're done with that, you can then, well, you would then do what we call a layout versus schematic. In PCB tools, this is often integrated. But it's a thing that checks for shorts, opens, makes sure that you connected everything you have in the schematic connected, make sure that you actually connected it like that in the layout, because this gets quite complicated. Sometimes it's very easy to make mistakes. And so it will then check that you connected everything correctly. If you connected everything correctly, then you will go to the parasitic extraction. And then from the parasitic extraction, it will give you a new netlist that you can then simulate again, and you can compare how much shift there was in performance.
I
And
would
now
be like super worried that I made some kind of silly mistake and it's not going to work.
Well, that's kind of the magic of this of using these parasitic extractions, is you are simulating what you've drawn. And so if it works with the parasitic extraction, you can be very, very confident it will actually work in real life, especially in analog. If you go to millimeter wave, things get much more complicated because the models become more troublesome. It's much easier to miss little things that matter in simulation but don't matter in schematic. But yeah, you can in general be very confident that if it works with a parasitically extracted schematic, it will work when you receive the chips back.
Okay, can we have a closer look on this chip? What are the layers, for example, or can we understand a little bit how this is created or what is inside of this file?
You mean this file here, or the
this file where we are designing the physical chip?
Yeah, okay. So if I turn everything off here,
looks like there are many layers.
yes. So this is just the used layers. Again, this is like in real technologies, this goes up to hundreds of layers.
Hundreds of layers?
Yes. Because you have lots of layers for all of your metal layers. For example, a 14 nanometer technology might have 12 metal layers. And then you have double patterning. So you might have more drawing layers than you have metal layers, because you have to draw multiple colors in one metal because of how the manufacturing works. And then you have all of your doping layers, because the chip is made by taking usually a P substrate wafer, and then to make N regions. So
do you have some
N-doped
pictures
silicon.
about
Yes,
this?
yeah, I have pictures of this. Right, so if you cut a transistor or a wafer in its length, right? So we're looking on the side. You start with this P substrate, and then what the foundry will do is they will make masks based on the things you draw, and then it will shoot N material, so a material with one electron too much compared to silicon. It will shoot those materials at the wafer to make these regions, these pockets where you have a different doping. It will then remove the mask, place a new mask for example, growing a gate oxide. It will then remove that mask, place a new mask, and so on to build up all of these layers. And that's how we make the transistors. So these are the two basic transistors that you have in CMOS, so the NMOS and the PMOS. And then the NMOS is literally just you take two N-doped regions, you place a gate in between, and now you've made a switch or a transistor. In the PMOS, what we first need to do is we need to make the substrate N type and then place P regions and then do the same. So this is the basic cross section of a transistor.
What is B?
And then that's the bulk. That's actually a trick question. How much pins does a MOSFET have?
It looks like 4.
It has 4. It has 4. In discrete, the bulk is usually tied to the source, and so this is connected together. But what this bulk does is it's actually connected to the substrate material. This should actually be P. It's connected to the substrate because you have electrons. You'll have electrons flowing here from this drain source region to this other drain source region, right? And they're also influenced by the material of the entire wafer, because these electrons, this substrate is conductive, and you might have other devices somewhere else on the wafer, and they're all interfering, and that's the bulk terminal. In general, you don't use this, and well, you don't use this in the sense that the bulk of a N type is connected to ground, and the bulk of the P type is connected to the supply. Because you cannot, if I now connect this to 0.2 volts and somewhere else I connect it to 0.4 volts, then I'm shorting them together, right? And that doesn't work. If you go to SOI, you can do very interesting things with these bulk terminals because then they become isolated. But that's a discussion for another time.
Okay, and in the tool, basically, there will be all these mask, they are really mask layers, which are applied during every single process to build this stack up.
Exactly. So actually, if you look here in the 45, this is more clear, right? But if you remember our cross sections before, right, we had this gate, which is I mean, you have an insulator with a metal on top, so that is this red zone here, right? So it's really just, this is the oxide, and then in the oxide, so this is the mask for the oxide. In this technology, they'll then use a different technology to indicate, look here, these contacts, you have to actually make a hole through the oxide to connect to what's underneath. We then place poly here on top to make that the conductor of the gate. So this is the terminal we connect our gate to. It's polysilicon, so it's a conductor. And then underneath, we say it's N implanted. So they then shoot N material at this, but they do this, in this case, after they've already made the gate. So the gate blocks the N from getting underneath the gate and only gets in the slots between. So this is what they call a self-aligned transistor.
So you need to also know all these processes to design it properly?
It helps. You need to understand what's going on. Because I can draw these layers myself without using the cell from the PDK. And as long as I draw them according to the design rules, that's fine. And the layout versus schematic tool will understand that this is actually a transistor that I've drawn, and it will work. And this is especially if you go to digital cells, they do this a lot because then they can really optimize for ultimate density where they place this contact in respect to the gate, or if they make the gate longer, and the polysilicon actually covers both an N transistor and a P transistor, because in an inverter, the two gates are shorted together, and they can do very interesting things with that. And then you wouldn't recognize these transistors like as easily as here, at first glance if you don't know what you're looking at and you don't know how they're made.
So basically the tool which is creating the parasitic schematic
Yes.
will also recognize all the kind of combinations of these layers, and it creates components from them.
Yes, exactly. So the layout versus schematic tool, it doesn't care that this is a cell that has been created by the foundry. It will just decompose it into the layers that it's made out of. And then once it's decomposed, it'll then look, okay, where is there a transistor here? How is this transistor connected? How big is this transistor? How wide is it? How long is it? And then it'll start looking, okay, can I now find in the schematic a transistor that is the same specifications, that is connected in the same way? Okay, it's this transistor. And it'll do this for all of your transistors, and then it will say, okay, it's the same or it's not the same. Yes.
I guess sometimes may happen it doesn't recognize it properly, and
yes, and then those errors are very fun to troubleshoot because it can get very confused if you did something wrong, and then it's a painful experience if that happens.
Okay, so now let's imagine we created this silicon. What do you do next?
So once you have your blocks made, so this would be an individual block, you then go to a higher level, right? So you use these cells in a higher level to make bigger and bigger systems up to the point where you have a chip. Then you connect your bond pads.
How do you do
which
that?
is the bond pads are just like the transistors. They're just a cell you get. I think I don't actually know if the GPDKs contain these. No, they don't contain bond pads as example. So you also
bond
just like the
pad is
transistor.
basically the place where you will be then connecting the wire to the pin of the chip. Okay.
Yes, and so this is also a cell that you get from the foundry, just like the transistor cells, just like the resistor cells, and so on in the PDK. They also have the design rules, so you place these bond pads based on how you want it to be connected in the package. Then you again go through all of these steps of verification, and then you send it out to the foundry. So you export just like a Gerber. In this case, it's usually a GDS2 format. You export this, you upload this to a file server of the foundry, because these are huge files. Sometimes they can be up to hundreds of gigabytes for very large digital transistors. And then they manufacture this for you, and then they send back silicon, or they send it to your packaging house, who will then package it according to your specifications, and then you measure it and you verify that it works.
Can you give some examples of the companies which are manufacturing these wafers, these silicons? I'm curious who is doing this.
So the biggest, most known is TSMC, Taiwan Semiconductor. And then they're one of the big ones. You have Samsung has a big foundry program. Global Foundries has a big foundry program. And then you have UMC, which is also in Taiwan. You have XFAB, which focuses mostly on automotive and older technology. So they don't have a 7-nanometer FinFET, but they will have a high voltage technology, for example, for a battery controller in an electric car. Tower Jazz in Israel, I think. They do a lot of they also do a lot of silicon photonics.
Why there is a shortage of the chips? There are so many.
That's because you cannot adopt a design, right? If I now make a design for a Taiwan Semiconductor technology, I cannot go to Global Foundries and ask, pretty please, will you make my chip?
So does it mean when, I think one of the companies, they burned down or something? I don't remember what was one of the problems.
I don't know if they burnt down, but an example, XFAB was hit by a ransomware attack, and they had to stop everything and restart a lot of processes. And that all of those customers, they're stuck. You cannot just take that design and quickly put it on a different technology. And so you're really tied. It's far less flexible than with a PCB design.
Okay, then they will make this silicon, and then what is happening next?
So then it has to be packaged.
So once you finish designing the chip, then you need to go here and continue designing the package.
Yes. I will just, so for example, we have here, this is the package design. So this here in the center, this would be a file you export from the chip design tool. And this is all of the different bond pads, or in this case, they use copper pillar bumps, solder balls, and you then import it just like with PCB design here, and you connect it to the BGA package on the outside. So the BGA balls, you do your routing just like you would in any other tool. So I just route it, connect it here, voila, add some vias, and so on, and then you do your routing, and then this is manufactured by a packaging manufacturer, a packaging house, which is sometimes the same as the chip designer, like the chip manufacturing house. Sometimes it's someone different. They assemble this and then they send that to you, or to your the board assembler, and then they mount this on the board on the PCB for testing, or for the customer.
So this package, is it based on like kind of PCB or?
Sometimes it is. So I think you can say that you have three big groups. So you either have your old school package, they'll call them, where you have like a DFN or a QFN, and then these are what they call lead frames. So this is a standard thing that you buy off the shelf. They place the chip inside, and then they use bond wires to connect the pins, and then they close it up. So that's
bond
one
wires,
option.
they like put there like gold.
Exactly, gold or
wires.
aluminum. Or yes, and so they connect the bond pads to metal pins on the packaging
But
frame.
then basically they can't follow this layout what you created here.
No, so then you need to use a different type of layout. So you first go, for example, to is there a nice, so you go, for example, here, this is a BGA with bond wires. So in the center here, this is the chip. And then around this, they've placed the pads on the BGA substrate. And then these blue, red, and yellow lines, these are the bond wires. So then the packaging house knows, like, I have to draw a wire from this pad, I have to pull it to that pad, so on. So they make this then for you, and then the chip is connected. This is now, in this case, it would be a custom package that you design in this tool, but you also can buy off-the-shelf frames where they have these pads always connected to the same pin. And then they do this for like this bond wire for you. You give them just a diagram of where the lines go. That's the first big group. The second group is a laminate-based package. So this is very similar to a PCB. You have a number of metal layers with prepregs and core materials. The main difference with PCBs is that the materials are much thinner and the lines are thinner. So a common package line width would be 20 micrometer traces with 20 micrometer gap, which if you go to PCBs, that's already very high tech. So you then draw it like a PCB, you make all of your connections. This is then manufactured just like a PCB, and then they place the chip on top, either with bond wires. So like in this example here, they would use bond wires where they put the chip with the pads upwards, and then they connect the wires.
Oh, I was thinking how it is actually done. So they put the silicon upside down and then.
Yes.
Okay.
And then, so that's one option. Or if you have solar balls on the silicon, then you put it with the solar ball on the package.
And then it is like soldered in oven, like standard components?
For example, yes. Yeah.
But
I mean,
is it done in higher temperature or otherwise?
Not necessarily.
Because I would expect the silicon like coming off or falling out from the chips if you.
Not necessarily, because there's after the soldering, they place an underfill material. So they place a glue underneath.
Okay.
That's then that then holds them together. And this underfill is like a science on its own. There's people, if you go to very large chips, so if you look at like a CPU die from Intel or AMD, you're talking about maybe 40, 50,000 solder balls on a single die. And they have to actually do, to some extent, simulations of how the underfill material will flow underneath the chip to make sure that it goes deep enough to hold the chip together properly under temperature loads and so on. Yeah, but
Wow.
so that's really the second group, and then the third group is what you now see with, for example, TSMC's CoWoS, which is where the packaging material, the packaging substrate is made in the same way as a chip is made. So it's a silicon or a glass wafer, and then they etch and plate metals and make oxides and grow it that way. And then you can get extremely high densities. And what you even see in industry is that they might actually not just do wiring, but you might have a CPU, and then in a 7 nanometer FinFET or a 5 nanometer FinFET, a CPU chiplet, and then you use the substrate material, you use like a older technology, a 180 nanometer technology, and they do voltage regulators and power management, clock generation in the package substrate. And then it's placed in the same way. You have solder balls or copper pillars that you place on top, and then you have a packaged chip.
And okay, so when you read about all these technologies in nanometers, 4 nanometer technology, 5, I don't know,
Yes.
what does it mean actually?
That depends. So up to like 20 nanometers or so on, it meant the gate length. So if we go back to my so for example, this is a 45 nanometer technology. I can place a transistor. I just here from the library, I say, give me one NMOS, please. I can now make the gate length here can go up to 45 nanometers. And so that represents this distance. So it's from this side to this side.
Mm-hmm.
And the gate length is kind of a determining factor in the analog performance and density. So to map that to our 2D view of earlier, right, it's the distance from here to there. That's 45 nanometers. And so up to about, well, bulk CMOS, so 20 nanometer bulk, that was actually the mechanical physical dimension that they make. So at the 22 nanometer technology, this distance is at least 22 nanometers. Or you can always go bigger, but you cannot go smaller. With FinFET, it's kind of a mess because when you have a fin, where do you define like you can define the width of a fin, but it doesn't actually correspond to any electrical specification of the transistor because the gate works in a fundamentally different way. And so they kind of gave up and they just make it smaller with every generation and they give it a smaller number, but it doesn't necessarily mean anything on the technology anymore.
Okay, now I'm confused. So what is fin?
And now then I have to quickly open a browser because I do not have. So an issue they had when they were making smaller and smaller transistors, right? So can I just open this LinkedIn? I don't know if that's a problem or not.
FinFET.
So this is the transistor I just showed you, right?
Mm-hmm.
If you look at it in 3D. So we have the gate, and then we have that source and drain region, and the current flows from the source to the drain. But the issue was, as you make this smaller and smaller and smaller, you run into leakage currents. So even if the gate is off, so the transistor is off, there's a small amount of current that flows from the source to the drain. And this is actually a huge part of the power consumption of like a CPU. It's just the fact that whatever you do, there's current flowing from the source to the drain. And then if you have multiple transistors on top of each other, it just flows from the supply to the ground. This is what they call static current or leakage current. And the only way to make that better is by making your gate longer. But you don't want to make your gate longer because if you make your gate longer, you can't fit as much transistors on a piece of silicon. And that's the thing that drives the speed. So what they did instead then is they wrap the gate around a fin. So they build a fin in 3D, and then they wrap the gate around it. And this way you can get higher density and better transistors without requiring more your physical area that is occupied by a single transistor to be larger. And these perform better.
And it's called fin because it looks like fins.
It's a fin, exactly. And then, I mean, when you go after that, they're now looking. I think TSMC for their next generation is going to go to gate all round. So then, what you do instead of having a fin is you have a little bar that is wrapped in the gate. So it wouldn't be connected here at the bottom. It would just be a little rod that goes from the left to the right, and you can then put multiple bars on top of each other to make more transistors. And that's gate all round. But that's in research. There's no one who I think commercially has this available yet.
Okay. And so what are the packaging companies? You mentioned sometimes the company which is making the wafers also will package the silicon and they will send you the finished chips, correct?
Yes.
Or you can you can also find like specific company which is only.
Yes.
Okay. Can we have some examples? I'm just curious.
And
how much this cost? Like silicon is expensive. Now you would like to put it into package. Is it going to cost again some money? I guess yes.
It's also expensive. So you're easily, for a prototype packaging run, you're easily looking at 50 to 100,000 US dollars.
Wow.
It's the overhead of chip design. It's expensive in low volumes because you need all of these very high tech masks. But because we make everything so small, you can fit millions of them on your or tens of thousands on a single wafer, and then you recuperate that cost after 10 million chips made.
But you need to be sure you are going to sell them.
Yes, you do. That's the problem. I'm not that familiar with packaging companies because the way that we do our packaging is that we have an intermediate. So we go to them and we say we want a package, and then they ask our specifications, and then they deal with which exact packaging house it's sent out to. And we often don't even know. So it's hidden to us.
Oh, okay.
So I know.
So basically, the company where you make silicon, they don't do it by themselves, but they will send it to their partners, or
exactly.
And you don't even know who they are.
It could even be that 1 week it's this partner, the other week it's another partner. And as long as it meets the specifications, it's fine. So yeah, it's a very difficult world to get into, I think. Yeah.
How did you learn all this?
By doing this as a job.
Because you look so young, like you just finished university.
So I'm now 29. So I first did my bachelor and master's in electrical engineering, and so now I'm wrapping up my PhD in electrical engineering. And so yeah, I've been doing this now for, if you say that I started at the start of my master's for 7 or 8 years. And you kind of have to learn all of this because you need to understand the different steps that go into making a chip to make good chips. You need to understand why you do certain things, why you don't do other things. But it's why chip design is fun.
Does it, or is it designed only by one person? So when you are designing chip, it's basically your chip, or more people are working on one chip?
I mean, in the context of a PhD, it's usually just your chip, and that's kind of the beauty of a PhD, is that it's why you need to know all of these things, is because you go through this flow. But at a company, I don't think this ever happens. And their design teams will range probably if you go to like analog devices and they're making an op-amp, those design teams might be a dozen of people. If you go to, for example, like Intel making a modem for 5G, I don't think Intel makes modems for 5G anymore, but or another company making a 5G modem, you might have literally thousands of people working together on one chip. But it's abstracted a lot. So the way that would work is that you have a digital team that does all of the digital design based on system specifications and system design that was done by a system team. And then that system team also has specifications, for example, for the RF amplifier, like the power amplifier block. And so you have an RF designing team that might be located in a different country in a different building that then does this block. You have specifications for the analog to digital converters that goes to the analog to digital converter team of the company, and so on. And then in the end, you have a top level floor plan team that takes all of these blocks and puts them together and does some final verification.
So
It might even
does it mean there must be someone who knows how to do everything?
not necessarily. I mean, to some extent, maybe, but not necessarily, because it could even be possible that I mean, it's often impossible to simulate the full chip, right? So you just have to rely on the fact that you know that if the RF team meets the block specs of the RF amplifier chain, that will work. And the same with the analog to digital converter team and so on. And then you make abstraction of all of this. All of the things that the top level designers need is just a block with here are inputs, here are outputs, similar to on a PCB, right? Where you don't know the individual transistors in your op-amp.
Yeah,
you just need to know what the pins are, and then they connect them together in a higher level. And so then that's how that flow would go. How much interaction there is, I would say, also depends on how advanced the chip is. The more advanced things get, in general, you need to know more and more things because you need to understand of all of you're working closer to the limitations.
So I know you are working on your own chip right now, correct?
Yes.
So what you are designing?
So we, my company, so the startup company that we do, is we have what we call polymer microwave fibers, and so we do the same thing that optical does by sending light pulses over a fiber, right, where it's trapped. We do the same, but then with millimeter wave signals. So signals in the range of 100 to 200 gigahertz. And so we use those for communication. So we have a cheap plastic fiber. It looks like this. I have one here. So this is what such a fiber would look like. It's just a piece of plastic. And then we use these antenna structures, like on the slide, to transmit signals in and out of those fibers, and we use them for communication, very high speed communication. So we're looking at 50 gigabit per second, 100 gigabit per second of data rates. And so we have to make our own chip because, I mean, you can go to a VDI, which is a company that makes millimeter wave blocks, and you can ask them make a transmitter that can do this for us, and then they'll say, okay, this is what it's like. It'll cost you $10,000 US, and it'll be this big. But what we want to do is we want to put this, for example, in cars or in data centers, and we need to make this cost $1 per chip or less, or well, per system. And the way we can do this is with by making our own chip. So we can make this 1.5 by 1.5 millimeters large. We can make it work on just 500 milliwatts of power by doing everything ourselves on a CMOS chip. And then because we make so many of them, if you sell them to a car manufacturer, they might make hundreds of thousands of cars, multiple, like 10 links in each car. So you're talking millions of chips. That cost of those masks is spread out over so much devices that they become very cheap. And that's why we do this on a single chip, and why it makes sense to do it on a single chip and to not try and make it with building blocks on a higher level.
So basically, this way you can replace the copper virus, and it's going to be even better because there is no like electro.
Exactly.
There are waves. So, but
yes,
there is no.
Yes. So I mean, you have, well, for one, galvanic isolation, which can be very interesting in a lot of markets, especially in cars, right? Where if you have like a high voltage battery system, one side might be at 400 volts and the other might be at DC. So it's completely isolated. We're robust to electromagnetic interference because at 150 gigahertz, the loss you have of your signals over a few millimeters or centimeters of air is so high that you don't have a lot of interference. And it makes it very robust. And then we're also, your engine noise, that can be an issue for copper communication, right? So spark plugs or in electromotors, the rotors and the high pulsing fields, their frequency content is very low compared to what we do. So it might be an issue if you're trying to use a coaxial cable. But for us, I mean, there's no spectral content at 140 gigahertz. So we can almost ignore this.
I think it's interesting idea. I have never heard about something like this.
Yeah.
So does it work? I'm just
Yeah,
curious.
I mean, so we have demonstrators in the lab from where we achieved 100 gigabit per second over I think 3 or 4 meters. So it works.
Wow.
Yeah.
So your chips are already manufactured.
Yeah, so this is not so I recently, my company sent out a new tape out. We don't have that back yet, but from previous designs, and also we've worked on this with the university. Yeah, we have this working. This is it's not a completely it's not the first time that we're doing it. It works. Yeah.
Cool. And so you designed the chip, but I guess in your team you have also these RF designers and all the other people.
Yeah, so my real focus is actually the RF design. That's what I came from.
You also do RF design.
Yeah, so these antennas that you see in the pictures, I designed those, and that's what I started out with. And it's only in the last few years that I've also started doing the chip design along with the rest of the team, because we need a lot of co-design. That was I was saying earlier, like if you're pushing the boundaries, you need to really understand all of those limitations. And so it's not like with an RF system at 2.4 gigahertz where you just have a 50 ohm output and you connect it with a 50 ohm transmission line. We optimize the antenna to have a certain impedance, and it might be completely different from 50 ohm. And then we take that into account with the chip side, that the chip matches to that antenna, or vice versa. We might see that the chip can actually provide much more output power if we have it matched at 20 ohm instead of 100 ohm. And then we try to design the antenna to match the 20 ohm and so on. So it's a back and forth process, and we simulate all of this in detail again. Like we bring
I
in
would
these
like to
S
just ask,
drivers.
what kind of software you use for these RF simulations?
Mostly HFSS.
ANSYS.
ANSYS HFSS. I've also used from Keysight EM Pro, which is their version. I've used from Keysight ADS, so the momentum solver. For the chip side, for the millimeter like simulations on chip with electromagnetics, we also use EMX, or I think it's now called Clarity or something from Cadence. Yeah, it depends also on the application.
You must be so clever. What else you have in this presentation? I'm curious. What did we talk about?
So,
or what we didn't talk about?
Yes. So this is also a slide that I think is interesting. It's why would you go for ASIC design? Right? And so one of the most common places where ASICs are used, I think, is, for example, automotive industry. So imagine that someone comes to you and they ask for a pressure sensor and they want a digital readout. Then that probably means you have to go and look for a pressure sensor chip. You add a microcontroller and so on, and you have lots of wires, lots of power. But what the automotive industry does is they have such a high volume, millions and millions of these chips, and they have very specific requirements when it comes to reliability. Their reliability requirements are insane, right? You're talking about part per billion failure rate over 10 years at 125 degrees Celsius. And so what you have is companies like Melexis, which is actually also a Belgian company. They will make a chip that does everything you need. So it includes on the same piece of silicon a MEMS pressure sensor, some digital control blocks, analog signal processing, memory. And so all they then do is they connect it to a package with 3 wires or 4 wires, power, ground, and signal. And then the Volkswagen or Bosch or whatever places it in the engine manifold to measure the pressure, and they just get a digital signal out. And because they have such high volumes, they can really make this chip specific to every single application. Tesla, for example, has a custom chip that is only used for that application in the sensing that someone presses the door handle, so the door handle can go open, because they have these door handles that are flush with the body, right? They have a custom chip for that. And ASIC is designed just to sense that, because it makes sense. Because if you are selling 1 billion of these sensors and you can save 0.1 cent per sensor, you're still adding up to hundreds of thousands of dollars that you're saving. So that's really where a lot of these ASICs sit, either
Are there
there.
many companies designing ASIC chips?
So that depends on where you draw your line of what an ASIC is, right? If you go really back into history, like in the 70s, they would say that a modern CPU is an ASIC because it's not made out of individual chips on a PCB with different gates, right? It's specifically designed to be a CPU, right? And the only non-ASICs I guess you would have nowadays is an FPGA that would not be an ASIC, right? But if you go to more modern, like turnkey ASICs, where you would have a customer with a specific requirement,
That's what
like
I
I
mean.
want this, right? You have quite a few of these companies. You have them both in the sense that you have, for example, Melexis, which makes this used to mostly focus on automotive, where a car company would often come to them, ask for such a design, and then there might be a kind of deal where after 5 years, Melexis is allowed to sell the chip to other car companies as well. So yeah, that would be one. You also have companies like IC Sense, which is also in Belgium, in Leuven, or Ansem, and they do turnkey ASIC design. So you, as a customer, go to them and they make for you a chip, and then you can put that into your digital TV decoder or your WWF, and you want to track fish, and you need a special sensor to track fish. So they make a special sensor for you. So I think
You give them
there's
10 millions and they will make special chip for you.
yes, it doesn't. It's not necessarily that expensive to develop. I think 1 million isn't.
Just 1 million. Okay, what do you have next?
I mean, this is a cross section of a bipolar technology. So what I mostly talked about today up to now is CMOS. But historically, and still for analog and RF, bipolar technologies are also popular. And then I mean, it's an NPN versus a FET. But
I can see this is a little bit more. It's not complicated. It's basically there are two processes, only two.
Yes. So the big downside of this is especially for digital is the standby current. So if you make a CMOS gate, right, which is shown here with an N and a PFET, and you think about logic levels, right? Either this input is a 0. If it's a 0, the PFET is turned on, and this NFET is turned off. So no DC current flows from the supply to the ground. And vice versa, if this is high, this device is turned off and this device is turned on. And again, no current flows. So in standby, in theory, if there's no leakage, this has 0 power consumption. And this is also how we can get these like chips that have femtoamp or femtowatts power consumption.
Oh, and bipolar, it's driven by current, so
yes, exactly. It's a current controlled current device. And so if a gate will always require some current to flow through it for it to work. And that makes it less interesting for digital design. And these currents on a chip, they might be picoamps.
But if you have millions of chips, it's going to be
exactly,
million
this
picoamps.
quickly adds up. Yes, so this quickly adds up. And so that's why outside of specific like analog blocks like op amps and so on, I don't think anyone uses a pure bipolar process. Because it just doesn't make sense to not have that low leakage. What you do see is what they call bi-CMOS. So that's when you have a CMOS process and they add bipolar transistors, or you have a bipolar process and they add CMOS transistors. So that's often used. For example, Infineon has a very famous, a very high performance bi-CMOS process where they have extremely fast bipolar transistors. They work up to 500 gigahertz or more, and then they have a very basic CMOS technology. So you can implement on your RF or your automotive radar, you can implement some digital control circuits to control the entire thing. So that's something you do see. But yeah, that's what was on this slide.
Okay, I learned something new.
And then I mean, this is CMOS. So the main advantage of CMOS is that it's instead of a current controlled current source, you have a voltage controlled current source. And because it's just a voltage, you don't need a power consumption to generate a voltage.
Yeah.
And so that's the big advantage. They also, but this is really an analog design thing, they have a bit less gain but you have two parameters to play around with as a designer, the width and the length, whereas for bipolars, you only have one parameter, which is the emitter length, which can be interesting, especially in very complicated designs that becomes important.
Mm-hmm.
I mean, this is a cross-section. We discussed this. And then here, this is a slide I had. So this is what a PCB level analog design would look like, right? So this is a schematic that I took from an Onkyo audio amplifier. And the big difference here is that I'm actually going to go to this slide here, is if you look here, this is how it's on PCB. You have lots of resistors and a few transistors. If you were to implement this on a chip, you would design it, as you can see here,
Mm-hmm.
you would design it without any resistors.
Mm-hmm.
Because, well, resistors are very bad, which we can come back to later. And because we can make all of the blocks that we want with transistors, and we can get a lot of transistors on a chip. That's the advantage of a chip. We can place thousands, millions of transistors on a single chip. So it makes more sense to use very basic transistor-based building blocks to build larger circuits than to try and use resistors and discrete transistors.
So you adjust the parameters of the transistor to have
Yes.
specific resistance? So
Yes,
basically
exactly.
you build in resistor inside of the transistor.
Yeah. For example, if you want a very precise resistor on a chip, you don't necessarily use a resistor. You could use a transistor and you bias it with the correct voltage, and you tune the length and the width to your desired size, and then it's a resistor, right? And you change all of those bias currents, the bias voltage, the size. Now it's a current source. You change it in a different way. Now it's just a switch, right? It's on or off, and so on. And so by doing this, playing around with these voltages and the sizes, we build out very complex building blocks with very basic devices.
How precise resistor you can make on chip?
With a real resistor or with a transistor?
Both? I don't know.
With a real resistor, it depends on if you calibrate or not. So if you really just place a resistor and you measure it, actually I have a plot of this, I did this earlier. So I placed a 100 ohm resistor in a simulation. So you can see here, this is 100 ohm, this is the resistance. And then I had it simulate with a statistical model of the resistor, 2,000 of these resistors, and actually see what the resistance is. And so you can see here, we have all of these circles is a resistor. We have resistors here that are 20 ohm, resistors here that are 260 ohm, 310 ohm. So it's a pretty bad resistor, right? And you can see from the statistical model here how much of these are, so this bell curve here of the average value, you can see how far it is outside of our target range of 100 ohm.
So how did you build this resistor on chip?
This is, I believe, a diffusion resistor. So what they do is they take one of these implantation layers and they just make it long. You put a connection on both ends, and then it's a resistance, right? Because there's some conductivity, and the dopant level influences that conductivity. More dopants is more conductivity. So that's one of the ways that they can make a resistor.
And because you can't really control these dopants,
very well,
dopants, then you can get like all the kind
yes,
of different variations.
Exactly. Or you can make it with, for example, some polysilicon, but then the thickness of that polysilicon is maybe not very well controlled. And obviously, if you make the resistive material thinner or thicker, then the resistance changes a lot. Because for making a transistor, the thickness of that gate is not vital, as long as the area is correct. And that's why resistors are so bad.
What
so
about capacitors?
Capacitors, we make, we can get them by adding metals, right? Making fingered devices. And they also vary a lot because your metal etchant might be a bit, I mean, on one wafer, it might be etched a bit more, on the other wafer, it might be a bit less, so your spacing is different. And what makes a big difference as well is the thickness of the metal. So you draw the width, right? But on one wafer, the thickness is 40 nanometers, on the next it's 37, and it's 45. And so that also results in variability. But I don't know exactly how, I don't have a quantifiable value for that.
Okay, I think this was interesting. Last time when we had a call, you mentioned each upper and upper layer, metal layer is going to be thicker and thicker and thicker.
Yes, I have that actually here in this slide. So what you have to, the blue is here, the metal layers, right? And you have to think that at the bottom here would be the active devices, right? So the transistors, they come down below. And so each of these is a metal layer. And so this depends on the technology, and often you have some freedom as a customer in this, right? But the very bottom metal layers, they're very thin. This is usually used for digital routing. So you want lots of local connections. Because they're thin, that means that they can make the minimum line width that they can etch also very low. So for example, you might have a 40 nanometer or 30 nanometer wide line that you can make with very narrow spacing, so you can get high density. But obviously they have high resistance, right? Because it's a very high wire. You might have ohms per square, like multiple ohm per square resistance. Then you go to higher metals, and now you're talking about maybe power distribution or connections of signals over long distances. So you need a bit bigger metals. And then you go to the very top, and there it's your supply plane, your ground plane, connections to bond pads, and then you get very thick metals. But because they're thick metals, you cannot make such fine structures in them. So you might have a logic device, like an adder, that is smaller than the minimum width of this top metallization layer. So it's hierarchical, and you route from the bottom upwards.
They do it intentionally thicker because they would like to use
Yes.
higher currents? Okay.
Yes, because this is actually one of the problems you have in chips is because your wires are so thin, you have what they call electromigration. And so the current flows through a wire, and the current flow is actually, it's electrons, right, moving through your wire from the negative to the positive terminal. And while they're flowing around, they bump into atoms. And every time they bump into an atom, they move the atom a bit. And before you know it, if your wire is too thin for the amount of current that's going through, it might actually bump so many atoms aside that you get a gap in your metal. And so connection that was made,
circuit?
open circuit.
Open circuit, sorry, yes.
I have an open circuit. And that's a problem. So you have rules for this. The foundry will provide you with a rule, for example, if it needs to work for 10 years, then you can send this much current per micrometer width of trace through this metal layer. And as you get to higher and higher metal layers, you can send more and more current through the metals.
So that's why the rules are so complicated, because they are also individual for different layers. Oh.
Exactly, yes.
Okay, what else do you have on these interesting slides?
Do I have a lot more? I mean, this is what a PDK is. This is an example here of, I should make this bigger. This is a model for a predictive transistor. So all of these parameters. So this is to give you an idea of just how much parameters a single transistor has. And so they model this with a lot of this like dependent sources, right? And then all of these parameters here, they tell the simulator how to model the behavior of the transistor in function of the voltages, in function of temperature, in function of currents, and so on.
Okay, I thought it's only it only depends on the thickness of the layers or something.
No, because there's even actually an effect that's called the strain of the gate, right? So I have here this transistor, right? And so this gate here, I'm gonna turn this layer off just to make it a bit clear. So I have this gate contact here, this gate poly, and I have here my drain and my source, right? The transistor behavior actually changes if I now were to do this. This is a very wide line. Let me try again. So if I start here and I connect this like so, for example, right? Now I place this metal one here in blue on top of my polysilicon. It's not connected, it's just above it. But the fact that it's there results in some strain on this gate, and it will move the transistor parameter. It will shift this a bit. And this can be a problem if I have a differential amplifier and I do this in one of the two transistors, but not in the other, then they become mismatched. And so This is also effect that a good parasitic extractor can actually model. So it can see this and it will tell you like, look, this is there's a VT shift in this transistor. And so this is why all of this is important in this layout. I forgot how we got here.
We got
Sorry.
here because you showed all the parameters of the transistor.
Exactly. Yes, exactly. So this might be something that is modeled in one of these parameters, is how this influences these things.
Okay.
It's even the case that the direction of the current on the chip might be an impact. So if current flows from left to right, the transistor might behave slightly differently than if the current flows from right to left, because of how the dopants have been patterned. And so when you go to precision analog design, what they will actually do is they will make sure that all of the currents in the transistors flow in the same direction.
We can go back to the presentation. And
okay.
What else you have there?
And then I just had this PEX. So I explained this, right? This parasitic extraction, finding all of these capacitors. So you have this model for, in this case, a FinFET. All of these specific like parameters are in this big file. This could be, I think, like 100, 200,000 lines of code that tell the tool how to model these parasitic components, and then it makes your new schematic, and you use that to simulate. So this is a 3D visualization.
So basically,
of that.
they are all these parasitic components. They are by default already included in the model. Just the values are calculated based on specific design.
So both. So you both have, for example, a transistor model that might include all of these parasitic capacitors up to metal 2 in the technology, and then above metal 2,
okay,
another tool has to take over and
so outside of the transistor you have another tool which actually find out where are all these parasitic. Okay,
exactly. What I then have is, this is a nice example. So this is what a terahertz chip looks like. This is made by a colleague of mine. And so on the right here, this is an antenna. I think this works. Oh, he's gonna be angry at me if I get this wrong, but I think it's 460 gigahertz. So this is your folded dipole on the right. This is a receiver, right? And then you have, here is a mixer. You have some amplifiers. You have an IQ demodulator as an IF, and then you go down. And I guess this is the output flows somewhere here, because then this is the LO chain. So you probably have you have two other mixers here somewhere. Dragon, don't hate me if I get this wrong. But this is what we design. If we do millimeter wave stuff, and you can really see the millimeter wave structures, right? So these are transformers. So we can make transformers on chip, and we use an EM simulator like ADS, like HFSS to model them. And then we include that in our simulation, our schematic simulation as an S parameter block. And then we can design this entire chip. And then you get it back from the foundry, and then you turn it on. You play a bit with the voltages, and then it works.
Nice. And you can show this, yeah, correct? No one is going to copy it.
I mean, just seeing this isn't going to be enough to copy it. And this is published. I specifically took a chip that is published in publicly available literature. This is why I'm not showing my own chip, because it's not published yet, all of them. So I cannot really show them yet until it is.
Patented or something.
Yeah. But what is also maybe interesting and worth noting is all of these, like if you look at these metal structures, right, there's all of these little blocks. And also here in these coils, we see these metal blocks, and this is what we call dummies. So one of the steps in making these metals, in order to make multiple metals on top of each other, they have to start from a flat layer. So what they will do is they will make a metal layer. They will then they will grow an oxide. They will etch inside of the oxide to make a trench that they fill with metal. And then they will use a polishing technique to make the entire chip area flat. And then they will make the next metal layer. But because when they polish, the resistance against abrasion of the metals is different from the oxide. And so in places where you have more oxide, it might polish and etch away faster than places with metal. And then you get wavy surface, which is not good. And so what the foundry will force you to do in their design rules is they will say, look, you need over an area of 10 by 10 micrometers, you need at least this percentage of metal. And then what we need to do is we need to add these blocks. Well, we don't do this necessarily by hand always. Sometimes we do inside of critical areas, but there's tools that do this for you. And they will place lots of these structures in between to make sure that your metal densities are correct and that you meet those DRC rules. Because
I think on PCB, sometimes they do it too. I don't know exactly. There is a specific name for this. I forgot how is it called.
I don't know how it is in the PCB world. I do know, especially with like flex, I think, and like HDI, this is important to have like correct metal densities, I think, in order to make it.
In large PCBs, they usually fill up this because you don't want like maybe bend the PCB or it's something similar.
And so this is a thing again that the foundry will specify. They will tell you what these densities are. And sometimes
is not this going to like influence the functionality of...
It will. And that's why you include this to some extent in the modeling. So you might, for some of these inductors and transformers, you might run another simulation after you add the dummies to make sure it's still correct, especially with where it's very critical if you have like a VCO inductor, where it might be very important to know exactly how that inductor behaves. You would simulate again with these dummies. But after a while, if you do a lot of this design, you start understanding when it will have a big impact and when it won't, and then you understand like, here I have to be really careful, or here it's okay. And there it's actually an advantage if you have a very wide band design, because if your bandwidth shifts a tiny bit, then it's less of a big deal than if you have a very narrow band. If you have a 100 megahertz bandwidth amplifier and it shifts by 200 megahertz, you have a big problem. If you have a 20 gigahertz amplifier and it shifts by 100 megahertz, then you probably don't care because you over design it anyways. Yeah, that's what a chip would then look like. I don't know if you have any more questions about this example.
We can move to different slide. What else do you have?
This is again that I have then, I mean, some examples of some blocks I found in literature. So this is an op-amp, CMOS op-amp here. Because what I really want to show here is how the power of CMOS is that we can use lots of devices. So instead of requiring a very precise device, we can use circuit techniques and lots of devices to get this to the same result. Right, and this is also what like if you look at modern op-amps, what analog devices or Texas Instruments or so on will do is instead of trying to make the perfect op-amp, they make an imperfect op-amp, but they include a digital block on the op-amp that allows them, when they package the chip, they test the chip, every chip is tested.
And they can tweak it.
Exactly. They then sometimes what they might do is even have like a special voltage signal, so that if they turn the voltage rail on and off in the correct way, they go into a calibration mode, and then the chip knows from the measurement how imperfect it is, and it compensates for this.
So it somehow uses different transistors, for example, or
exactly,
or it changes voltages or something.
Yes. So for example, you might have you need a very precise resistor, 100 ohm. So instead of making 100 ohm resistor, you make an 80 in series with a 25 in series with a 5 and so on, and always smaller. And you add switches that allows you to bypass these resistors.
And
then you measure it, and then you figure out which switches you have to turn off and on. And that way you make a precise resistor. And what you can then even do is, if you know how the resistor changes versus temperature, so you have a resistor that has to be a 100 ohm over all temperature ranges, right? And so you have two options as a designer. Either you buy a very expensive, or you build a very expensive resistor that is completely flat over temperature. Or what you do is you take a resistor that might not be flat over temperature, but you know how it changes over temperature, and then you add on your chip a temperature sensor, and you add a bit of digital circuitry that can then, from the temperature, understand how it has to enable or disable certain parts of the resistor to make it larger or smaller to compensate for the temperature. And by doing that, you can, with much smaller area, with much cheaper devices, get a better performing transistor, resistor.
how they program then this circuit? Are there some pins which are not, or can you somehow connect directly to silicon and program it before you actually place it inside of the package?
That is one possibility. So that's something that is done. So they might have special additional bond pads that are not connected to the actual frame, but when they do the assembly of the chips, they have a probe card that lands, has like maybe 1,000 pins that lands, and then can measure this chip in big automated test systems to measure that resistance and then program in the value. That's one option. Another option is, this is for instance done sometimes on automotive sensors that I know of, is that they actually have kind of hidden modes. So by on top of the supply rail, providing certain pulse shapes, the chip kind of enters a calibration mode, and then suddenly for example, the analog input, instead of being an analog input, it's a digital input, and you can program in the calibration values. And then what you might do is either you just assume that your customer never knows what the key is to get in, and you just leave it at that. But you can also then tell the chip itself to blow an internal fuse on the programming array so that it can never be changed. Maybe you don't want, for example, a statistical anomaly to make your temperature sensor enter a programming mode, right? That's and so that's another way. Sometimes it's just hidden registers on the chip that you might like not be visible to you through I2C, but when the chip is powered on for the first time is, and then again once it's programmed, they blow up the fuses. These are all options, and it goes all the way to like with a CPU, right, where you have the ability to program new microcode to tell the CPU what to do after the fact, and you can even add patches, and Intel will give you, or AMD will give you security updates.
Okay, so this is what the microcode does. It actually configures this internal circuit which will adjust the chip parameters.
Part of it, yes.
Wow, okay, nice. Okay, what else do you have? I think we are finished.
Yes, that's what I had prepared for today. And then I have the resistors.
Thank you so much, Joren. This was like super interesting. I never knew how all this flow goes, chip designing flow, how it goes. So now I have idea how it can be done, and it looks to me even more complicated than designing PCBs.
There's one thing I didn't touch on today, and that's ESD, which is a very big deal in chip design. But we can keep that for another time.
Yeah, okay. Yeah, it used to be a big problem, I remember, but I think now many times
it's a bigger problem still. It's just now it's fixed by the chip designers.
Because there are these protection diodes, no, or something.
Yes. So diodes is one way that they do it. It's the old way, I think. The usual way that you do it now is with SCRs. So like or transistors that will switch on if the voltage gets too high and then short of supply rails together. That's another way that they do it. But yeah, that's and this is something that they also design too, because for us, for example, at millimeter wave frequencies, this is a big problem in high speed IOs because you add a lot of parasitic capacitance. And so one of the things we have to do is we have to actually add big structures with inductors to compensate for the capacitors to get a flat response, and to tune out our ESD diodes.
But that's good because I don't use chips very often. I try to handle the boards the way as customers may do it, so no ESD protection or anything. I really would like to find out as soon as possible if there is sensitive chip, and then I never use it.
The problem is like with ESD is that a lot of people think it's a binary condition, right? So either a transistor has or hasn't failed. But what you actually see with ESD is that it's mostly strain damage. So you have an ESD event happening, and now your chip, instead of working 10 years without failure, it will work for 1 year without failure, right? And you can't, it's very hard to measure or to figure out that this happened. Imagine you're assembling a car module, and because of a defective machine, 1 in 100 chips has this ESD event. They all still work when they leave the factory, but now 3 years later, 1 in 10 of these cars is failing because these chips are dying, right? And that's why it's very critical to really understand this design. And it's why you have companies whose only job is to design these blocks for chips. So for example, in Belgium, we have Solfix. They make ESD diodes for customers. So you go to them and you say, this is our application, and they will make a structure for you, so you can be confident that it works.
So basically then you use it as a from the library, as block from library or something?
Yes. And this is, I mean, these library blocks are also done with analog design, right? So for example, in my case, we're a millimeter wave design company. We don't want to spend, well, use one of our engineers to design voltage regulators for an entire year. So instead, what we do, there are big IP catalogs from the foundry. There are companies who make voltage regulators, and we pay them, for example, either we pay them once and we can use this forever, or we pay them per die we sell a certain amount of money, and then we can put their voltage regulator on our
How do
chip.
they count how many chips you sell?
I don't know. I suspect it might work through the foundry. So the foundry knows what cells we place on our chip, and so they can count that way. I suspect I'm not that familiar with using these IP blocks and how that exactly works. But that's, yeah, it's something that happens a lot. Or you might have an analog chip, an analog team, and now we want some programmability. We're not familiar with digital design, so instead we just buy an I2C module block from a library and we place it on our chip. It comes with a data sheet, just like a regular component on a PCB does. These are the inputs, these are the outputs, this is how it works, and then we use it.
Oh, that's good you mentioned this, because I think it helps to understand more complex designs. So you can buy IPs and you can just use them on your silicon. Yes.
Or you can have them be custom made as well, right? That's also an option, right? You might have a company who makes, you pay someone to do this design for you and build you a block. That's also an option.
Okay. I think we covered everything today. So thank you very much, Joren, for all this information, and I really enjoyed this call.
You're welcome. I also had fun. I hope I was a bit coherent.
It was great. It was really, really cool. Thank you.
You're welcome.
And that's everything. Thank you very much for watching this video. By the way, we are preparing some very interesting tutorials, so if you don't want to miss them, hit the subscribe button. If you want, you can also check out our FedDevel online courses, where you will find everything important from basic board design up to advanced hardware design and PCB layout. The link is in the description. That's all for this video. Thank you again. Don't forget to leave your comments, and see you next time. Bye.